Okay, so still in optimization problems. Here's the first question we're going to do. A rectangular box with a square base is to be constructed so as to have a volume of 1 cubic meter. Okay, that's what we want to do. Okay, so 1 cubic meter. Find the height, or find the dimensions. Let's call this like this, of such a box if the amount of material used is to be minimal. Okay, and the box has an open top. Okay, so this is the question. Okay, so basically we have a box like this. With an open top, okay? And you know that the volume inside, right? The volume has to be 1 meter cubed. They're asking you, what should the dimensions be if you want to use up the minimum possible material to create such a box? Okay, so of course, I drew the box like this. I could have drawn it like this as well. Okay, this is also a square box with an open top, and I could make it so that it has a volume of 1 meter cubed. But which dimension will make me use up the least possible material? In other words, I want the surface area to be at a minimum. Okay, so this is the function that I'm trying to minimize, is the surface area of this box without the lid, right? Without the cover. Okay, so what we're going to do is we're going to label the sides x, x, and y. So x and x, because we know that the base is a square. It tells us that it's a square base. Okay, and the height is y. So what's given to us is that the volume is 1 meter cubed. So the volume of a prism volume is x squared. So area of the base times the height, x2 times y, and this is given to us that it's 1. Okay, so far so good, this you got, I'm sure. Okay, which means that if I want to isolate y, so y is equal to 1 over x2, because I'm going to need that. Okay, so what do we want to maximize? I mean to minimize. Okay, so we want the minimal material. In other words, we want to minimize the surface area of the box. Okay, that's what it's meant when they tell you use the least possible material. In other words, the least possible area. Okay, so I don't know if the box will be this shape, or I don't know. That's what we're trying to figure out. Any questions until here? Okay. So what's the area? So the area of a prism is, so I could just count each face. Okay, so each face here, my pencil, each face here, so this of course is x times y. Okay, and of course each of these, there's 4 of these. So 4 times xy plus, and there's just one base, because it's just the floor, there's no ceiling, it's empty. So the area of the base, which is the area of the square, which is x2. Any questions on how I got this? All good? All right. So this is what we want to minimize. So I'm going to now express this function in terms of x only. So I have to get rid of the y. How do I do this? By using this relation that's given to us. Okay, so a is equal to 4 times x times y, which is 1 over x2 plus x2. And so a is 4 over x plus x2. This is the function that gives me the area of the prism as a function of the size of the base only. Any questions? Am I going too fast for anyone? Okay, good. So now what? I need to minimize this function over what? I need to find what are the possible values for x. Okay, so what's the smallest possible value of x? Of course, it's 0. Well, almost 0. Okay, if x is very, very small, the y is going to be very, very big to get a volume of 1. Okay, so we're going to start it from 0, and of course, x could be very, very big. It could go to infinity, and the y will be very, very small. So there's no limit on the x. Are we good? Okay, so of course, at 0, it's not really interesting, because at 0, I know that the volume will be 0. Okay, it's a flat. It's a tube. It's a very thin tube that has absolutely no volume. Okay. So let's find the a prime and put it equal to 0. The derivative would be -4 over x2 plus 2x, and that's equal to 0. If I send now the 4 over x and 4 over x2 on the other side, I'm going to just move up the paper a bit. Okay, so I get 2x is 4 over x2. Send the x2 up here. I get 2x cubed equals to 4. Divide both sides by 2. I get x cubed equals to 2. And then I'm going to find the cubic root to get the x. And so x is equal to the cubic root of 2.
Sir, why do we find the derivative?
Oh, I'm sorry, I can't hear you. Why did what? Sorry?
Why do we find the derivative?
Why do we find the derivative? Because we said that in order to determine where a function has a maximum or a minimum value, it is important for us to see where is the derivative, in other words, the slope is 0. You remember?
Yeah, okay. Thank you.
No problem. I can't hear you loud. Maybe it's me. Okay, we'll see.
Sir?
Yeah.
What property did you use to find a derivative of 4 over x, like without doing any work?
Of 4 over x?
Yeah, how does the derivative turn
Do
into
this?
negative? Yeah.
Okay, so so let's see how we got this. I'm gonna do it right here, okay? So 4 over x prime is the same thing as 4 times x to the minus 1 prime. And then I use the product rule, the power rule, put the minus 1 in front, minus 4x minus 1 from the exponent is minus 2. And so that's negative 4 over x2.
Thank you.
Clear?
Yeah.
Okay. Okay, so now I have the x, and so now I should be able to find the y. Okay, so how do I find the y? I have to plug in the x back into here, because that's how I get the y. Okay, so y will be 1 over the cube root of 2 to the power of 2. So basically 2 to the power 1 over 2 to the power of 2/3. Good? Okay. Now the only thing I need is the only thing I need is to find the area of at these values and see what we get. Okay, so I'm not going to check at 0 and I'm not going to check at infinity. I could, in fact, because if I plug in 0 here, I'm going to get infinity, and if I plug in infinity here, I'm going to get infinity. So the area will be infinity if I put any of these bounds, but it's not that important for now because these are limits to evaluate, and that's not the point here. Okay, open interval, I'm just interested in this value. So A of the area of cube root of 2, what will be the area here? So 4 over the cube root of 2 plus cube root of 2 squared, so 2 power 2/3. This will be the area. Okay, and what will this give me? Let's calculate it. So I think I get 4.76. Is this what you get? I don't know if I have the answer. Oh, I do have the answer. Let me check. Yeah. Okay, so I get 4.76. Okay, now my question is, and it's an important question, how do I know if this is, so this would be the area meter squared, right? This is the area. How do I know if this is a maximum or a minimum area? Okay, I found the critical value. So basically I found that at 4.76 I have a slope of 0, but I still don't know if it's a situation like this or a situation like this. Okay, so how will I know this? Do you understand the problem? Okay, so this could happen to you on the test, and you end up with this, and you have to decide whether it's a maximum or a minimum. So usually what we do, we plug in this endpoint, we plug in this endpoint, and you plug in all the critical numbers and see what's the max and the min, like you're going to do in the assignment I sent you, the worksheet, and like what we did in class last time. Okay, but there's another way to do it. Okay, and I'm going to show you now. Okay, so let me write down.
Yes, sir.
Yes.
For the function for area, you put in the y value, but shouldn't you have put in the x value?
What?
Like you put plus 2 to the power of 2/3, but shouldn't it be plus
This here?
no, the next number.
This?
Yeah.
Oh, no, it's because it's squared.
Oh, okay, yeah, I see.
Okay, it's squared. This is this value. This is to the 1/3 power 2, so it's 2/3. Yeah.
Thanks, sir.
Check, but we got it right, I think. Okay. Questions? Anybody doesn't understand what we're doing so far? Okay, please let me know.
Sir,
Yep.
how come to find the area you didn't use like the first one before the derivative? Oh, you did. Okay, no.
Okay, so I'm getting suggestions on how to decide if this is a maximum or minimum. So I'm getting suggestions in the chat. Maybe use the function of A. Well, that's what we use. I use the function of A. I got that. So yeah, that's what I got. So theoretically, if I were to plug in the cube root of 2 into this function, into A prime, I should get 0. Okay, which means that I'm at a horizontal tangent, either here or here, I don't know. Now, how do I know if it's basically open downwards or open upwards? Okay, so I'm going to write this down here, unless you have suggestions. If not, I'm going to do it, and it's going to help us a lot with the curve sketching.
Can't you just plug in numbers before and after?
Good, that's a good idea. It's a good idea, but and it's probably right in this case. Okay, but yeah, it would be good. It would be a good test. You could do like this, right? It's a good idea. You would go, and we're going to use this when we do curve sketching. Okay. So my problem here is, you know what? I'm going to do it on a different page because I'm running out of space here. Okay. I'm just going to write. I'm going to take another page and write the important information that we have here. Okay. So 1 second. So the question is, so first of all, we found that A of x, so the area as a function of x is 4 over x plus x2. That's one thing we found. Another thing we found is that A prime of x, we know, is -4 over x2 plus 2x. This we know. Then we found the critical number. We just found one. We found as cube root of 2. This is the critical number. Okay. So now the question with this information, how do we know whether A reaches a maximum or a minimum at x equals cube root of 2? This is the question I'm trying to answer now. Okay. So there's two ways. Okay. One way is what has just been suggested, which is very good. Okay. Is to go like this. I will do sort of a table. And I'm going to put the values of x. And x goes from, of course, 0 to positive infinity. And somewhere here, there's one important, there's a lot of values, but one important one is this one. Cube root of 2 is an important value. Okay, and I'm going to see what a prime of x is worth here. A prime being the derivative. Okay, so I know that if I plug in the cube root of 2 in a prime, I'm going to get 0, right? Because that's how I found cube root of 2. Okay, are you with me, or it's too fast? You with me? Okay, so again, at x equals cube root of 2, a prime is 0. We know that because this is a critical number, and that's how we found it. Now, what we could do is plug in a number that's bigger than cube root of 2 into a prime and see if I get a positive or a negative number. And then the number before that and see if I get a positive or a negative number. Okay, so let's take a number that's bigger than cube root of 2. So cube root of 2 is what? $1.26. Okay, it's about 1.26. So let's plug in 2. Okay, 2 is bigger than 1.26. Let's plug in 2 in here. What do I get? I get -4 over 4 is -1. And -1 plus 2 times 2 is 4. -1 plus 4 is 3. So that's going to be a positive number. You with me? So it means that the derivative after cube root of 2 is positive. And let's put a number that's less than cube root of 2. So for example, 1, that's an easy one. Let's plug in 1 into here. So -4 over 1 is -4. -4 plus 2 is -2. Oh, that's negative. Good? Questions? Anyone? You have to ask me a question if it's not clear, please. I could restart the whole problem from here. From here, I could restart if you want. Okay, I don't mind. If you lost or if you were distracted.
Sir, I have a question. Why are we putting the critical number into the derivative and not like the function of a?
You could, if you put it into the function of a, if you put this critical number in the function of a, that will give you the exact area when x is this. Okay?
Yeah.
But what I'm trying to find now is it's true that the area here will be 4.76. Okay, it's true. But I want to know, is it going to be bigger? Is it a smallest value or a bigger value? If I take a value a little less than that and I plug it into a, will I get something less or more than 476? You understand?
Kind of.
Kind of? Okay. Okay. There's a few ways to do this. Okay, so one way is to see the function is like this. Okay, so I'm going to draw a. Okay, so I don't know what a looks like. So this is x and this is a. Okay, basically, what I know now is that if x is equal to the cube root of 2, well, the y will be right here at 4.76. This is what I know. You understand? You agree with this?
Yeah.
Okay, so now my question is, okay, good. Is my graph like this? Or is my graph like this? That's what I'm looking for. That's what I want to know. This is what I don't know. I know for sure that it is either a valley or a hilltop, for sure, because the slope is 0. I found this by asking that the tangent is 0. You understand?
Mm-hmm.
Okay, so now I'm trying to figure out. What is the graph? What does the graph look like? Like this or like that? So one indication is that if I plug in 0 into A, I'm going to get infinity. So I'm like this. And if I go to infinity, it also goes to infinity. So look, it looks like it's going to be a minimum. It looks like it. Okay? Or else I would have gone to minus infinity and like this. It would be like this. Okay? But that's not enough for me. Okay, okay. As in it's enough, or okay?
Yeah.
Yeah?
Yeah, thank you.
Oh, it's Anna?
Yeah.
Good. So what did I just do here? Okay, so this is very important because I plugged in my critical number into a prime, and then I checked a test point before, a test point after. I found negative, positive. So what does it mean when the derivative is negative? It means that the function is, that means that the slope is negative, and therefore the function is decreasing. Do you understand that? Okay, and if it's positive, it means that the slope is positive, means that the function is increasing. So that's enough for me, because now I know that before this value, the function is decreasing, decreasing, decreasing until here, and after that, they start to increase, 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 increase. And so it's definitely a minimum. Is this okay?
So, sir, if it, let's say, like the number before cube root 2 would give you a positive slope, and the one after would give you a negative, that would mean it would be the maximum.
Of course, because that would mean that the function would be increasing here, decreasing here, so you'd be like this.
Okay, thank you.
100%.
I have a question, but if it gave you like a maximum, how would you find the minimum?
If it gave you,
If it's telling you like minimize it?
I don't understand what you said. If it asks you for,
Because like it's asking us to minimize
yeah,
it, but what if happens if it gives us the maximum? Like what would we do?
if it asks us for the maximum, right? Or if it gives us, I don't understand. If it,
Well, because the question is, can you like minimize it, like find the minimum number? But what happens if,
no, wait, no, the words are important. I'm not asking you to find the minimum number. That's a wrong sentence. I'm asking you for the number that minimizes the area. It's not the same thing. You understand the difference? I'm asking for
yeah, but what happens if it gives us the max?
What does that mean? What it means it gives us the max.
Like what happens, because you told us to verify that it's the minimum, but what happens if we verify it and it's the maximum?
Then it's not, that's not the answer, but then there's no minimum. If in this question, let's say in this question, they would ask us what dimension would give you the maximum area. That's your question? Is that your question?
Well, I was just asking if it's asking for the minimum and then we do the verification and tells us like that's the maximum.
Okay, so if it asks, let's say it asks us find for the minimum value, and then we do this and we get something like this, up and then down, that's what you're saying?
Yeah.
Okay, good. That means in this case that the function would have been like this, right?
Yeah.
Okay, that means there's no minimum.
Okay.
In the same way that here, there's no, if they would ask me what is the maximum, I'd say there's no maximum. Nobody stops me from creating a box like this. Okay, do I have space? Yeah. I could create a box like this. Look at this box. Can you see this exaggeration? You see this box? Well, it's a really ugly box. Okay, it's very, very thin and long. It's like an infinite long stick with almost no volume inside. Well, no, not almost no volume, with a volume of 1. The volume is constant at 1. But nobody stops me from stretching the box like a spaghetti and making it very, very as much material as I want. You understand? Amanda, you asked the question?
Oh yeah, I understand.
Okay. 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 Let's get this. Okay, so now I see clearly that this is a minimum. So A has an absolute minimum at x equals cube root of 2. Okay, and so indeed, this is where at these dimensions, right? The dimensions would be, let me try it again. Well, that's to move up a bit, I think. Okay, so this is, by the way, the first way of determining whether it's a maximum or minimum, and you're going to use this a lot in curve sketching at the end of the course. So this will be my answer. Okay, that's an open box. So this. Okay, so this will be cube root of 2. This will be cube root of 2, and this was what? I forgot. 1 over 2 power 2/3. Okay, this would be the height. Okay, so at these dimensions, this is how you're going to use the least possible material. Good. Okay, there is another way to determine whether at this point we have a function that is open upwards or open downwards, and this is what we're going to use a second derivative. Okay, so so another way to determine whether A reaches a maximum or minimum at x equals cube root of 2 is to use what we call the second derivative test, which we're going to do much deeper in curve sketching, but might as well introduce it here. Second derivative test. Okay, and what is that all about? So we find the second derivative. So the second derivative, so I have it, so just let me write, it's -4 over x2 plus 2x. This is a prime, so prime, right? This is a second derivative, will be, so 8 over x3 plus 2. Okay, so this is my second derivative. Okay, so the first thing we do is we find the second derivative of the function, and then we're going to plug in our x into it, okay, and see what we get. So a prime prime of cube root of 2, what do we get? Okay, so I'm going to plug it in here. Oh, this is going to simplify nicely. So I'm going to get, if you get cube root of 2 cubed is just 2. 8 over 2 is 4 plus 2 is 6. Okay, and let me explain to you what this 6 means in 2 seconds. Go finish this first, so make sure you're done writing, because I'm talking too much and too fast. Okay, you're done? Okay, so the second derivative test is as follows. Is that if a prime prime of x is 2 possibilities, if it is greater than 0 and if it is smaller than 0. If it is greater than 0, means that the function is concave up like this. And if it's negative, means it's concave down. Okay, that's what it means that the second derivative is positive, okay, and negative. So positive, happy, negative, sad. Okay, that way you won't forget it. Okay, so in this case, as you see, it's positive. So since it's positive at that value, it means that the function is concave up, it's happy, and therefore we have a minimum. Okay, so it's another way to determine whether you have a maximum or a minimum at a certain critical number. Any questions? Okay, so you're gonna see there, I didn't, you should ask a question, what happens if it's equal to 0? And that's a good question. And that's called an inflection point, and this we're gonna do when we do curve sketching. For now, I'm just focusing on when we have a minimum and a maximum, and it really, I don't think it will happen that I'll give you a problem where there's an inflection point in such a word problem. Are there any questions? All good? 100%? Okay, let's do another one, okay? We don't have much time, but at least start it. Okay, let me see what I could find here. Let's try this. These are the very typical questions. Okay, so what we call a Norman window. Okay, just make this bigger so I can see the read. Okay, has the shape of a rectangle surmounted by a semicircle. Surmounted by a semicircle. That's what a Norman window is. So if the perimeter of the window is 15 meters, find the dimensions of the window that will maximize the amount of light admitted. Okay, so do you understand the question? Okay, so I'm just gonna at least draw it for you. It's always important to draw. Okay, so there's sort of a semicircle here. Okay, something like this, basically, okay? And we know that the total perimeter here is 15. We want to maximize the area. Okay, so we have about 3 minutes left in the class. So I have 2 questions. Should I do it for you now, or you want to try it at home and maybe I give you the answer and we'll do it tomorrow? Yeah, it's better? I think it's better to try it. Okay, so let me give you the answer. At least you won't work for nothing and you could validate what you got. Okay, so the dimension. So here's the answer. So it would look like this. One second, I don't get their answer, to be honest. Oh, okay, good. Yeah. So it will be like this. Right, so this will be 15 over 4 plus pi, and this here will be 30 over 4 plus pi. Okay, so obviously the radius, so you also need the radius here of this semicircle, which is of course going to be half of this. Okay, so these are the dimensions of the window that lets the maximum light in or has the biggest area.